Okay, so it's recording. Welcome everyone back to part 2 of lecture 12 of the course Quantum Theory in a Nutshell. So before the break, we just discussed the representation of an operator A hat as a matrix. And in order to do so, we made use of this resolution of the identity, and we wrote this operator using the basis E1 and E2 for the vector space that our quantary state leaves. So um, um, so now that we have an operator A hat, um, this is in the context that we are discussing. This is a 2 by 2 matrix. So I can act with this operator on a cat. And remember, a cat is a column vector. So if I act with a 2 by 2 matrix on a column vector with 2 entries, I get back a column vector. So the product of a matrix, a 2 by 2 matrix, with a 2 entries column vector, gives me a column vector. So A hat acting on a state C will give me back a cat. And this cat I will call C prime, okay? So if I, let me move. So, oh, sorry. So if I define A hat multiplying C, this will give me a cat that I'll call C prime, okay? And now I can play again with the insertion of identities, okay? So you see that I have an operator times a vector. So I can come here and in this space between A hat and C, I can insert an identity, right? Nothing forbids me in doing that because A hat times the identity is just A. So I'm not changing anything. So I insert the identity between A hat and C. And again, I will replace the identity by the resolution of the identity in terms of the projectors. So I insert an identity here, and then I write this identity as being the sum of the projectors. So between A hat and C, I will have the butterfly EI, EI. And this, you see, I'm pulling out the sum because these are linear operators. So I can always enter with these operators in sums or remove sums from the line of action of this operator. Okay, so now let's pay attention to what I'm going to do here. I have an outer product EI acting on a vector. Okay, so by the definition of the outer product, I can take this bra, multiply by this cat, and this will give me a number, right? We saw that earlier in details. So a bra times a cat gives me a number. And being a number, I can place it wherever I want because the number will commute with everybody. So I take the bra EI, multiply by the cat C, I get this number, EI times C, and I'll just pull this number in front of A, okay? So I just multiply this guy by this guy, and the result I wrote here, okay? So I repeated the sum, then I wrote the number that I got out of this first part of this product, and the result is just A hat acting on EI, which I repeat here. Okay, so from this part to this part, I just used the definition of the action of the outer product on a vector, and just took the number and put in front of everybody. Okay, so the new vector, yes, is there a question?
Ruby. Hey.
Okay, it was not a question. Uh, so I just wrote the vector C prime as being A hat acting on C, and then I just say, look, I can put an identity here, and I just wrote the identity using the projectors, which is the sum of the projectors, and then I just use the definition of the outer product. This gives me a number times a vector, and the number I put in front of everybody and kept the vector here. You see that I cannot move this vector around because there is a matrix multiplying it. And the multiplication of a matrix and a vector is not commutative. So you cannot replace the orders, okay? But this number I can move because this is just a number, okay? Now, look at this, and this start to become a game of inserting identities. So I look at this expression and see, look, I have A hat acting on EI. But in the previous page, I just defined an object which is the sandwich of A with two E's, one cat and one bra. Here I just have A and this bra, and this cat. This bra is already multiplying this C, so I cannot play with this bra anymore. So what I do, I come here and I insert another identity. And when I insert the identity here, I will have this butterfly, EJ, EJ, and I have to insert another sum, okay? So be careful. I had this sum, and now I have another sum that takes over these projectors here. So now I have a cat EJ, a bra EJ, that multiplies A hat and EI. But this sandwich, EJ, A hat, EI, we know, we gave a name to it, and we call this, so here it appeared as, if I had the index I and the index j, we call this aij. Here I have the index j and the index I. So I will call this aji, okay? So this sandwich is the same quantity that appeared in the previous slide, but I have to put the indices in the correct order. So here comes first the j and then the I. And you see that this is a number, okay? This is a vector contracted or being acted by a bra. So this is just a scalar, okay? So again, as a number, I can place it whatever I want. So I will call this number AJI, and I'll put this number in front of everybody. So I put it here. And in order to simplify the notation, instead of writing bra E times cat C, I will call this as CI. And C, I have to put the I here because this has the index I. So I have to label this by some index I. And this number and this number, they multiply the cat EJ, which I repeat here. So all this thing started with cat C prime as an operator A hat times a cat C. From here to here, I just played with insertions of identity. And the result is that I can write C prime as a double sum of a number times another number times EJ. And what is the nice thing about that? Well, I just expressed the new vector C prime in the basis that I know, right? So when you learn about vector spaces in linear algebra, you always want to express vectors in a given basis. The basis we are working with is the basis of the vectors EI, which is E1 and E2. And this expression here tells me how to write the vector C prime in the basis of vectors E. And you see that I just obtained this expression by inserting projectors. So in many calculations that you're going to do in quantum mechanics, you have to do this type of gymnastics. You have to insert identities here and there and just contract things and get numbers out of that, numbers that multiply the cats of the corresponding bases. Okay? Sorry, my voice is dying. So I will just clean a bit this slide. But you see that, so I invite you actually to look at these expressions and try to reproduce them. So take a piece of paper and try to do these calculations that are explicitly written in these slides so that you are sure that you understand every step that I take here. This is the only way of learning these things. Okay? So, very good. I'm saying that the cat C prime can be expressed as this combination of numbers and vectors E. But it's also a trivial statement that C prime, so irrespective of doing all these manipulations, you know that if you have a basis, you can always expand C prime in this basis, right? So what I do here, I just write the obvious thing. C prime can be written as a linear combination of the vectors that form the basis. In particular, I'll have this coefficient that multiplies Ej, and this is nothing but the expansion of the vector C prime in the basis of Ej. But this is nothing but what I have here as well. And since this is basis, the coefficient that appears here must be equal to the coefficient that appears here, right? This is the beauty of writing a vector as a sum of vectors that form a basis, because you can compare coefficient per coefficient. So I have to declare that the coefficient of Ej here is the same as the coefficient of Ej here. And you see that here I define the bracket EIC as being CI. Here I have EJ C prime. So in analogy to what I did here, I will write it as CJ prime. So by comparing this expression with this expression, I can write that CJ prime is the sum of AJI times CI. And you see that I have a sum here because I have a double sum here. So one of the sums that will appear here will compare with one of the sums here, but there is another sum inside here that I have to write here. This is not confusing. I mean, if you think, because when I say these things and point to something that is already written, it sounds like confusing. So I say C, J, and then E, J, E, I, and so on. So these are all very confusing language. But again, you cannot forget what is the starting point. The starting point was to write C prime as A times C, and then I just played with the resolution of identity and wrote C prime in the basis of EJs. And then I'm just saying, well, I already knew that I could expand C prime in the basis of EJs, because EJs, they form a basis, and as a basis, I can expand any vectors as a sum of them. And then I just compare the coefficients, and this is the result. So what this is telling me is that I know how to relate these coefficients C prime with the coefficients C, which correspond to the coefficients of the expansion of C, of the vector C in the basis E. Okay, let me see the questions. Where CJ comes from? The CJ, you mean? So this is, I'm just giving a name to this quantity. And you see that if you have a vector, so let's assume that you have a vector. So let's think about standard vectors. If you have a vector V, you can write it, if you are in a plane, you can write it as the component of the vector in the direction x plus the component of the vector in the direction y. Okay? And I'm just saying that, so if I take now the scalar product of this vector with x hat, this will give to me x hat times x hat, which is 1. So this will be Vx. And x hat times y hat, which is 0, because they are orthogonal. So I'm just checking that Vx, the component of V in the direction x, is nothing but the product, the scalar product between x hat and the vector V. Okay? So what I'm doing here, I'm just writing this expression, the same expansion here, but in Dirac notation. So I'm saying C prime is the coefficient that comes with the element E1 plus the coefficient that comes with the vector E2. But who is the coefficient that comes with the vector E1? Well, just follow the rule here. The coefficient is the scalar product between the basis, the vector of the basis, times the vector itself. So this will be E1 times C prime. And this will be, sorry, this will be E2 times C prime. Okay? So you see that the coefficient that appears with E1 is the scalar product between E1 and C prime, as the coefficient in the direction x hat is the scalar product between x hat and the vector V. And this I am calling C prime 1, and this I'm calling C prime 2. Okay? As I call here Vx. Does this answer your question? So there are two questions, one by Yusra and one by Mahmoud. I think the explanation somehow works for both, but I want to know if it's clear okay, so you two understood what I said. Okay, good. Okay. So I'm just telling you how to relate the coefficients C prime with the old coefficient C. These can be written in a matrix notation. And this matrix notation is the following. The vector C prime is the matrix A hat times the vector C. So I can write the vector C prime as a column vector. So C1 prime and C2 prime. These must be equal to the matrix A hat, which is, as we already saw, A11, A12, A21, A22, and this must be multiplied by the vector C, which is a column vector, which is nothing but C1 and C2. Okay, so now I can act with this 2 by 2 matrix on this column vector, and I will get this column vector here. So if I multiply this matrix by this column vector, I will get a column vector with those elements. So just by equating the first entry with the first entry and the second entry with the second entry, I can read off who is C1 prime in terms of C1 and C2, and who is C2 prime in terms of C1 and C2. You see that it's a combination of C1 and C2 times these coefficients of the matrix A. So in the end of the day, I'm just telling you that given an operator that acts on a vector, I know what will be the entries of the vector that is produced by this multiplication. Okay? And this is written here. Okay? Good. Now I'm going to introduce to you an important concept that is actually very important for what comes next, which is the concept of a Hermitian conjugate operator. Okay? So far, we are considering operators, and the only thing that I essentially demanded about these operators is that they are linear operators. So if you act with this operator on a sum, then you can act with these operators on the parts of the sum separately. And now I will start making the class of operators that I'm interested about more restrictive, okay? And there is one particular class of operators, which are the operators which are called Hermitian operators, okay? But before I define what is an operator which is Hermitian, I have to introduce the concept of Hermitian conjugate, okay? So I will introduce this notion now. Consider an operator A hat, okay? So I define, so this is a definition, I define the Hermitian conjugate of this operator A, and I denote that by A and this symbol, which is some sort of crux. I define that as, and the symbol is called dagger, okay? So I call this operator, which is the Hermitian conjugate of A, as being A with the dagger, okay? And how is it defined? It is defined by the following. So if I have the sandwich EJ A hat EI, you know that if I mean, this is a number, and this number is equal to the complex conjugate of this number here, where A dagger is the Hermitian conjugate of A. Namely, this is the operator that when I compute this number and take the complex conjugate, I will obtain this result here. So this is a very abstract definition. We are going to see a more practical one. But in the abstract way, the Hermitian conjugate operator is the operator that you have to insert here in order to get the same number as you got here. If you take, so actually you have to be careful because there is also the exchange of the orders of the vectors. So this number will be equal to this number with the complex conjugate if you insert the A dagger here. Okay, but what does it mean in terms of practical language? It means that you see that here I have the element Ji of the matrix A, And here I have the complex conjugate of the element ij of the matrix A dagger. So when you exchange the there is a question: is dagger canceling against this Hermitian, this complex conjugate? No. I will explain that. Okay. Um, um, when you have a matrix that, so I think for your question, I think the answer can be yes, depending on what you're asking. But I will come to that, and maybe it will be clear to you. So if I have a matrix, imagine that I have a matrix which is A11, A12, A21, A22. You know that there is what we call the transpose of this matrix, which essentially means transform this row into a column and transform this row into a column. So I have now a new matrix, which is A11, A12, A21, A22. This is what we call the transpose of this matrix. And you see that I obtain the transpose of a matrix when I exchange rows and columns. Okay? So if I have the element in the row 1 and column 1, well, if I exchange row and column 1 by 1, it is not affected, so it remains here. Now, I have sorry, there is something in the chat. This, I didn't understand what was meant. But anyways, it seems that the issue was sorted out. If I exchange the row and column for this element, this is in row 1, column 2. If I exchange the order, this element will be row 2 and column 1. So this becomes this element here. Okay? And if I proceed with the same logic, this element will become this element, and this is also invariant, so it stays here. So this is the transpose of a matrix. Okay? So you see that if I think of A here as a matrix, I'm taking the element Ji of the matrix A hat, while here I'm taking the element Ij of the matrix A dagger. So you see that here I am exchanging the orders of rows and columns. So I'm somehow taking the complex conjugate, sorry, not complex conjugate. I'm taking the transpose of the matrix, okay? And here I'm saying another thing. After taking the transpose, you take the complex conjugate. Okay? So the element Ij of the matrix A dagger will be the element Ji of the matrix A complex conjugate. So this gives a very practical and handy way of defining, of writing the Hermitian conjugate of a matrix. So if I give you a matrix A hat with entries A11, A12, A21, and A22, I can write the Hermitian conjugate of the matrix A by taking the transpose of this matrix. So I'm taking the transpose of this matrix. So I'm putting this element down here and this element up here. So this is what I did. A12, A12, A21, A21. And then I take the complex conjugate of everybody. Okay? So this is how you obtain the Hermitian conjugate of a matrix A, which is denoted by A dagger. You transpose the matrix and take the complex conjugate of everybody. This is how you do it in practice. And you see that this operator will satisfy this relation here. Okay? So when I give you a matrix, a square matrix, I ask you, what is the Hermitian conjugate of this matrix? It is easy. You just transpose the matrix and take the complex conjugate of everyone. Okay? So this is how you take the complex conjugate of a matrix. And there is also an important thing, which is the following. Let's assume that I can obtain a cat C from the multiplication of a matrix B times another cat B. Okay, so C, which has the column representation C1, C2, is obtained by the product of this matrix B1, 1, B1, 2, B2, 1, B2, 2, with B1, B2. So if I take the product here, I'll have this row multiplying this column. So this will give me big B11 times B1 plus big B12 times B2. So this is the first element. And I take the second element, which will be B21 times B1 plus B22 times B2. And here is the second element. So the cat C is written as this combination here of big B's and little b's. Okay? Before I continue, let me see. There is a question in the chat. So is it wrong to say the transpose of Hermitian conjugate? I don't understand the question. So what do you mean by is it wrong to say the transpose of the Hermitian conjugate? The Hermitian conjugate is the transpose of the matrix with the elements taken, the complex conjugate. But maybe you can elaborate more if you want. Yeah, so now I see your point. So when I write a dagger, what I mean by that is the following. You take the matrix A, and you take the transpose of the matrix A, and then you take the complex conjugate. So inside the operation of taking the Hermitian conjugate, you are already transposing the matrix. Okay? But nothing forbids you to take the transpose of this matrix, right? This is a matrix as any other, so you can take the transpose of that. But the operation that I call Hermitian conjugation is this one. You take the transpose and then take the complex conjugate. Okay? You're welcome. Good. So I just wrote C as being, when I write C as the operator B acting on the cat B, I just wrote the components of the vector C. But remember, we learned how to write the bra if I know the cat, right? So when I had a cat, let me call it alpha, and we had entries alpha 1 and alpha 2. I told you, if you want to write the bra associated with this cat, you transpose the vector. So this will be a row vector now. And you take the complex conjugate of each entry. So this is how you obtain the bra from a cat. Here I have a cat, and I know the components of the cat. So I can just take the bra associated with this cat. The bra will be, again, I have to transpose this vector and take the complex conjugate. So the first entry will be this whole sum here. So the first entry is this whole sum, and I have to take the complex conjugate of everybody. So this will be B1 star, B11 star, plus B2 star, times B12 star. Okay? And these are numbers, so they commute. I can change the order here. And the second entry of the bra C will be this element complex conjugated. So I can just take the complex conjugate of this element and write B1 star, B21 star, plus B2 star, B22 star. Okay? So the bra associated with the cat C is given by this expression here. But this, in turn, can be expressed as the product of this row vector and this matrix, this 2 by 2 matrix. If I multiply this row vector with this 2 by 2 matrix, I obtain this row vector here. And you see that this vector is nothing but the bra associated with the cat B. So I transpose B and take the complex conjugate, times this matrix here, which is B11, B21 and not B12, and B12 and not B21. Everybody complex conjugate. So this is nothing but the transpose of the matrix B and complex conjugate. So this matrix here is the Hermitian conjugate of matrix B. Okay? So what I'm telling you is that if you have a cat C that is written as an operator times a cat B, you can compute the bra associated to C by doing the following operation. You write C, the bra C, as being the bra B times the Hermitian conjugate of the matrix B hat. Okay? So now when I give you an operator O acting on a vector alpha, and I ask you what is the bra associated with this, well, you write bra alpha O hat Hermitian conjugate. That's how you map the bra associated with this cat. Okay? So this is a very important rule that you have to know. Given a cat C that is written as operator times cat B, the bra C will be the bra B times the Hermitian conjugate of B. So if I have a cat and I want to inverse it to become a bra, I inverse the order of B, but multiply by the Hermitian conjugate of the matrix B. Okay? Now I can also have two matrices, and I multiply these two matrices, A and B, and I want to take the Hermitian conjugate of the resulting matrix, right? Well, if you take a 2 by 2 matrix and multiply by a 2 by 2 matrix, this will give to you a 2 by 2 matrix. So I can now take the Hermitian conjugate of the resulting matrix. And you can show that the Hermitian conjugate of the product of two matrices is, you have to invert the order, you have to write BA and take the Hermitian conjugate of each matrix. It's like the transpose, right? If I have a matrix A and a matrix B, and I want to take the transpose, this is equal to B transpose and A transpose. You need to invert the order and take the transpose. Okay? This is, maybe there is a connection issue with you. Okay, I see that you are rejoining little by little. Um, so at the moment, I see 22 participants, including me. So, I mean, essentially half of the class, I mean, disappeared in this issue that you had. It seems to be a bit unstable. Okay, so I think I will do the following. I will just finish with the explanation, and you can watch this last 5 minutes or so in the recorded version, because it's. I mean, I or I can just end the class here, because I mean it's a bit. Yeah, I think you are having more problems because the numbers are still. I mean, now the numbers are too low. So, um, is there anyone around so that I can give you some message? Okay, so I will do the following. I will stop the lecture and we continue tomorrow, okay? Because we just have a few minutes and I don't want you to miss this part. Okay, so I will stop recording and we continue tomorrow. Yeah, unfortunately, but yeah, this is the one of the challenges of remote teaching. Okay, bye-bye.